Okay, here's what we're going to do. We're going to go through the entire VCE Chemistry Units 3 and 4study design before the exam on Tuesday to make sure that you've got everything up to scratch. You can use this as either a checklist, which I'm doing with all of my students, or you can do it as a quick review as well if there's some things that you might have missed or you're a bit overwhelmed with the entire course. It's a big course. So we're just going to go through the entire thing. I'm going to explain things relatively quickly. I'm going to try and keep this under an hour. I don't know how I'm going to do that, but we're going to see. We've got a checklist here, which is actually a checklist that I've used for, I just created this for all of my students. I did it on Notion. So basically it just breaks down the entire study design dot points into individual little skills and questions that they check that they know that they can expand on. And then they rate them from either forgotten, can remember, can use, or can apply. And obviously one of my students already filled one of these in. This is just a copy of theirs. And in their final shoots, we're just going to work through anything that they're still not sure of. And that's pretty much it. So we'll jump right into it. So basically I've organized them by topic. I'll try to timestamp them as well so that you can jump to the particular areas or outcomes that you want to look at. But the first one, we're looking at fuel. So can you define a fuel? And so I've already got notes in here as well, a chemical source of energy. That's all you really need. It's pretty unlikely they'll actually ask that. Distinguish between a fossil fuel and a biofuel. So remember that fossil fuels are not renewable fuels. Biofuels are renewable, but not necessarily sustainable. The correct definition though, fossil fuels come from naturally occurring resources that are non-renewable, and that's why they're called fossils. Biofuels are from organic matter, right? So you got to remember, biofuel is not defined as a renewable fuel. It's defined as a fuel made from an organic matter. So that is decomposing plant or animal material, or from animal material or plant material. So things like bioethanol and biodiesel. Distinguish between a sustainable fuel and a non-sustainable fuel. So that is where we're looking at the rate of consumption is going to be greater than, a sustainable fuel will have a rate of consumption less than or equal to the rate of production, so that way then you'll never run out if it is truly sustainable. If it's non-sustainable, it's the other way around. Remember that not all biofuels are actually sustainable. If you look at bioethanol, for example, made from the fermentation of maize crops, although it's renewable, it's not necessarily sustainable because then the impacts in terms of the land use and the water use and the destruction of habitat to sustain it is then going to mean that we don't actually have sustainable production in terms of its impacts. And as well as that, the amount of demand, if we were to completely switch all of our energy demands straight towards the use of bioethanol, we would not have the ability to produce it at a high enough rate. Explain the origin and renewability of different fuels. We've kind of already done that one there, but so going through each of them, you need to know like what they're made from, whether they're made from coal, crude oil, that kind of thing. You also need to know things like coal seam gas being a form of methane gas that's taken from pockets of methane under the Earth's layers, usually under ocean beds and that kind of thing. I'm expecting they'll probably do a coal seam gas question this year because they have not done that in previous years. As well as that includes the origin and the renewability of biofuels as well, and then also other types of green energy sources. So looking at like solar energy, wind energy, hydro energy. You don't really need to know much about the specifics of those. So then can you convert between kilojoules per mole, kilojoules per gram, and megajoules per ton for enthalpy? So there's a really quick trick, kilojoules per mole. I'll actually scribble here as well. I've got just a whiteboard behind here, which I'll jump back and forth between. So kilojoules per mole to kilojoules per gram to megajoules per ton. The idea is here you're just converting moles into grams. You just multiply that by the molar mass, but really what you're doing is because you're multiplying the denominator by the molar mass, you're effectively dividing that enthalpy unit by the molar mass, whatever it is, 1800 kilojoules per mole, divide it by the molar mass of the fuel, you've got it as kilojoules per gram. Then from there, megajoules per ton. So with this one here, we're technically having to divide grams by 1,000,000, and then we're dividing kilojoules into megajoules, so we're dividing by 1,000, but that already kind of cancels out, so you end up with dividing the denominator by 1,000, which is equivalent to just multiplying by 1,000. So really, divide by molar mass times by 1,000, you've got your conversions. You can divide and times backwards as well. There we go. So then moving along, can you write a balanced combustion reaction including states and enthalpies? I won't go through the specifics of these, but remember that you just write down the fuel, oxygen, and then carbon dioxide and water vapor. Although technically you put liquid as the state, remember your states. And then you balance carbon first, hydrogen second, and always balance oxygen last because you've already got pure oxygen there, which means you can balance oxygen at the end, won't throw everything out of balance. If you get a fraction like 15:2 in front of the oxygen, double the entire reaction. You don't want fractions in your final thing. Sometimes I've seen them that like maybe they accept it. It's safe to always go with whole integers though, every time. Do you know the difference between complete and incomplete combustion? So that really is just when you don't have a proper oxygen supply, then you have incomplete combustion, which makes carbon monoxide and water vapor, whereas complete combustion, you get carbon dioxide. That's it. Put those down, balance it as normal, it'll sort itself out. Definition then of a gas pressure and its units of measurement. They've got this in the study design. We don't really see this much in the SACs or anything. So definition of a gas pressure is the force per unit area expressed or exerted by gas particles in a container or on the container's surface itself. Units of measurement, pascals is the technical standard unit, although we really only see pascals being used in the gas law, which is coming up next. And in that, it's kind of converted and used in kilopascals anyway, so you don't have to convert to pascals. The R value is already kind of factoring in that. So the universal gas law, PV equals nRT, you'll pretty much be asked to use this in some kind of question, probably from the fuel stuff as well, because gases are evolved from it. So N is number of moles of the gas that you're looking at, P is its pressure in kilopascals, V is its volume in liters, R is the gas constant, which is given in the data booklet, 8.31, and then temperature, remember, is in Kelvin, not degrees Celsius. Standard units for temperature in science is Kelvin, so add 273 to degrees Celsius, you'll have the Kelvin degrees. That's it. Otherwise, you're just rearranging and solving. Remember as well that you also have the shortcuts. If something's at SLC, then the molar volume is 24.8 litres, meaning 1 mole occupies 24.8 litres. So you can actually work out numbers of moles of a gas at SLC by doing the ratio of the volume you have to the molar volume as well. Calculating heat energy released from the combustion of fuels, and this is just stoichiometry basically, straight from that. So you've got, I'll write these down over here. So Q, or heat energy, is going to be number of moles times enthalpy if it is in kilojoules per mole, otherwise mass times enthalpy if it's kilojoules per gram, and obviously if it's megajoules per ton, multiply by the number of tons, you'll get the amount of megajoules of energy being released. That's pretty much it for that one. So each of these is really small, right? It's breaking up the dot points into lots of little pieces. Then the next one is, can you draw and label energy profile diagrams? These ones usually people don't have a lot of trouble with. So if we just put them down, we'll go there. So we've got an exothermic like this. If it's catalyzed, it does that. If it's endothermic, it'll go up like this. Really, it should curve like that, but I've seen them sometimes just kind of jump straight up. And again, if it's catalyzed, it'll do that. So this is endo and exothermic like this. So this, in terms of labeling, this is your reactants, this is your products. The gap between the reactant level and the peak is going to be the activation energy, EA, and the difference between the start and the finish is going to be the delta H. That's your enthalpy. You can see it's a drop, so therefore delta H is negative for exothermic. All the same stuff on endothermic. Always remember that the activation energy of an endothermic is not greater necessarily than the activation energy of an exothermic, because we don't have units. If the units are arbitrary, this could have been something like 50, and then this here could have been like, I'll break the scale and make it all wrong, but 1,000, or let's just go 500 and 1,000. It's a little bit out of whack, but there we go. Activation energy is 500. If I put this as 1 and this is 5, activation energy is only 4. So just because it visually looks bigger doesn't actually mean the activation energy is bigger. Depends on the scale itself. Cool. So then, can you use stoichiometry to calculate the volume of gases emitted from the complete combustion of a given amount of fuel? So this is kind of similar to the amount of heat energy, more stoichiometry, right? So if you've got, it's technically just straight up stoichiometry, so you can get the number of moles of the fuel that you have, then you can use the combustion reaction, you can balance the equation, then do the mole ratios to get the number of moles of the gas evolved, and then you can use PV equals nRT, or the molar volume if it's SLC, and work out the volume that's being evolved from it. Then define specific heat capacity. So this is the amount of energy required to raise 1 gram of a material by 1 degree Celsius, or you could say 1 degree Kelvin, won't make a difference, and it's measured in joules. the energy, so therefore it's joules per gram per degree. It can also be quoted as kilojoules per kilogram per degree, but the number doesn't change because both the energy and the mass have gone up by a factor of 1,000. So for water, 4.18 we need to know. It's on the data booklet as well. Using the specific heat capacity of water to determine energy released by combustion of a fuel. So this is Q is equal to MCAT, right? Q is equal to MCAT, like this. So mass of water, not the fuel, because it's the mass of the thing that you're heating. This is the 4.18, and this is the delta T, that is T final minus T initial. With differences in temperature, you don't need to convert to Kelvin necessarily. You can just do the difference between them in degrees Celsius, because Kelvin is just 273 units higher. It doesn't have any factor of scale or anything in it. So we do that in like calorimetry and stuff, but you can also use it as a measurement of energy released from a particular fuel. Pros and cons of fossil fuels, including all of these, and then the pros and cons of biofuels in relation to energy, content, renewability, and environmental impact. So the real main thing is all of the fossil fuels, they're all generally relatively cheaply available. They're pretty accessible, but the problem is that the supply, the downside is that they're not renewable. They also have severe environmental impacts, and they're not sustainable as well. We cannot continue to kind of extract them the entire time. With the biofuels, the benefits to them are that they are renewable. The downside is they're not always sustainable, and they often still will pollute because they're still carbon-based. So biogas, for example, methane, sure, you can get it from organic matter or from living organisms, but you cannot get it to not release carbon dioxide when you burn it. Same thing with bioethanol, same thing with biodiesel. So that's relation to energy content, renewability, and environmental impact. In terms of their energy content as well, most of them have relatively comparable energy contents. If there's going to be a trade-off though, we generally see that the thing that is less sustainable, that is fossil fuels, often are a little bit more potent than the biofuels, but it varies from one to the other. You've got all of that information in the data booklet anyway. Can you explain the relative benefits of petrodiesel for transport over biofuels? So we generally use petrodiesel for transport. The main reason for that is because of the high viscosity of biofuels and also the hygroscopic properties of biofuels, making them thicken up in cold temperatures, and that when water droplets get in there as well, it can thicken up the actual fuel, block the fuel lines, and it doesn't work, which means in icy and cold conditions, it doesn't work very well at all. So we prefer to use petrodiesels in things like submarines, ships, and that kind of thing. And then for cars and other forms of transportation, we generally go for petrodiesels. Petrodiesels in those, we can use biofuels for, we use that for like agriculture and that kind of thing. So running tractors and that kind of stuff. Then we've already done that, discussed the implications of hygroscopic properties in biodiesel and the implications of viscosity. So the resistance to flow is viscosity, and it's quite high in biodiesel. Discuss environmental impacts of the sourcing and extraction of petro and biodiesel. So environmental impacts, petrodiesel, we can extract this from coal and oil products, including crude oil. And so therefore there are significant environmental impacts, particularly with fracking and drilling and that kind of thing. With biodiesel, the problem with that is that it's a huge demand on land use, which means you have to excavate land and probably destroy a lot of habitat for ecosystems, which is a big problem. It's also relying on the commercialization or the production of vegetable oils or animal fats. Ethically, we don't really use animal fats because if you can get it from a plant where there are no ethical considerations, why not? But the downside to it is that then you have to repurpose a lot of land for the sake of crops and agriculture rather than, say, housing, or more likely greenery and natural ecosystems and that kind of thing as well. So these are some of the environmental impacts. On top of that as well, biodiesel still pollutes, right? It's still carbon-based. Can you define redox reactions? So that's it for the fuels. Keep in mind as well, I forgot out in that actual list, biodiesel extracted from triglycerides. So you take triglycerides, you remove the glycerol by hydrolysis, you then take the fatty acids and digest those, and then they become the biodiesel. Petrodiesel, you get that from methyl esters, and you pull off the methanol from the carboxylic chain, and then you take that chain and then turn that into your petrodiesel. So then, can you define redox reactions? So redox reactions, I doubt they would ever ask you to define it. It's literally just the combination of a reduction and an oxidation reaction put together. They always work in pairs. Can you calculate oxidation states to determine reduction and oxidation half reactions? So they often get you to determine if something is a redox. And so basically, if we take like a nice simple one, right? Like Fe to Fe2 plus and 2 electrons, we can clearly see this is in the 0 state, this is in the 2 plus state. Therefore, it's increasing, therefore it is oxidation. You can also see electrons being removed there. But you can also take it like, for example, if we went SO2, hopefully this works out well, and then I'll go with like H2SO4, we'll see what happens there. And we'll look at the sulfur. So the sulfur here, ignore everything else, I'm going to leave out all the other stuff. We always assume hydrogen is +1, oxygen is -2, unless we're trying to work itself out. So this is 2 lots of -2, plus whatever S is, has to add up to 0. So therefore we can just do it as algebra, right? 2 plus -4 is equal to 0, so S is equal to 4. Oh, that looks like 2 negatives. There we go, so S is equal to the 4 plus state. Over here, then we can see that we've got 4 lots of -2, so that is -8. Plus sulfur, which we don't know, plus 2 protons, so 2 plus has to add up to nothing. So 2 and -8 makes -6, plus sulfur is equal to 0, so sulfur now is in the +6 state. Like that, we can clearly see that's gone up, and therefore that's oxidation as well. That's pretty much the skill that we're talking about there. Then, can you write balanced half equations for oxidation and reduction? So with that one, all you do is you just write the reactant and the product. So technically I've got a half reaction here, right? I've got my reactant, I've got my product. Then you add water to balance the oxygen, or you should always balance the non-hydrogen oxygen. Add water to balance the oxygen. So we've got 2 oxygens over here, 4 over here. So I'm going to add 2 waters to balance the oxygen. Now I add protons to balance the hydrogen. So I've got 4 protons over here. I've only got 2 over here, so I'm going to add 2 protons. And then finally add electrons to balance charge. So here there's all neutral. Over here we've just got a +2, so I'm going to add 2 electrons. And there's my balanced half equation. Done. Can you distinguish, or can you write balanced overall redox equations? I won't go through that one in detail, but basically you just look at the electrons that are being transferred between the oxidation and the reduction. If they're off by a factor, cross multiply them until the electrons are the same, add everything together, the electrons cancel out. You might have some protons and stuff cancelling out as well. Then can you distinguish between primary and secondary cells? So primary cells are non-rechargeable, galvanic only, they can only discharge. Secondary cells can both discharge galvanically and recharge electrolytically by charging or putting in an electric supply. Can you label all features of a galvanic cell, including anode, cathode, electron direction, anion direction, cation direction, half equations, and overall equations? So with those, if we were to set one up, 2 beakers like this, put our salt bridge in, we'll put our, it's really messy, but oh well, doing it nice and quick, right? So then we've got our electrodes. The idea is that wherever you've got electrons leaving, you have oxidation, and so therefore you have the anode. The electrons then migrate towards the cathode. And you can use the trick red cat oxan. Always works because it works in both galvanic and electrolytic. Always reduction at the cathode, always oxidation at the anode. So the electrons are going that way. What that means is because you're losing negative charge, you're going to have anions moving through the salt bridge and migrating towards the anode, and then cations moving towards the cathode, like that. And then you'll see something like this. You'll see something like H2 and H plus or something. They usually write them just like this. And then over here, I don't know if this would actually react properly or whatever, but there we go, copper and copper solid. And the idea is that if you've got any gaseous or aqueous mixtures where there's nothing solid, then you'll see that the electrode is either going to be carbon graphite or it'll be platinum as well, just so that you've got something physical to attach to it. So there we go. That's everything there. Then can you explain the role of the electrolyte and the salt bridge? So technically the electrolyte is to allow the balancing of charge. That is, the anions move towards the anode to balance the loss of electrons. The cations move towards the cathode to balance the gain of electrons. The salt bridge is the physical bridge that allows the electrolyte to flow between the two. That's it. Explain the energy conversion in galvanic. That one's an easy one. Chemical into electrical, no issues there. Compare the energy conversion in galvanic to exothermic. This is a weird one they've got in the starter design. So basically all it is in galvanic, the reactants are not in contact with each other and you're converting chemical to electrical, whereas exothermic, the reactants are in contact with each other and you're getting chemical to thermal. Use of electrochemical series to predict the spontaneous reaction that would occur under certain conditions. So with this one here, I don't actually have an exothermic, get my words right, an electrochemical series in front of me. But you can always use the rule of left over right and right over left. So with galvanic, left over right. What that means is if you have a bunch of series, I'll just say that like this is my left side, this is the arrows, and then this over here is the right side. I just highlight everything that I actually have on the left. I highlight everything that I have that's on the right side species, and then I look for the two things that are highest on the left, lowest on the right. So long as my left hand is higher than my right hand, I have a spontaneous reaction, and they will go ahead. That is for galvanic. The further apart they are, the more spontaneous they are, because then you've got more entropy, you've got more chaos or more disorder, because you've got more energy being released the further apart they are. Remember that the voltages on the side of the potentials are the measure of the energy difference between them. So that's it. So higher up, reduction, lower down will oxidize. When you're doing electrolytic, it's all flipped the other way. Then you want right over left, and you want them to be as close together as possible. But be careful, because even though they're visually close together, you've got to check that the voltage difference between them is the smallest, because that would be the most effective. That'll be the one that goes first, not spontaneously. You have to put energy in, but the smaller the energy difference, then the less electricity it takes, and so therefore that one will go first or preferentially. Then determining half-cell equations from the electrochemical series. So that one is kind of what we've talked about, right? So you isolate all the species that you have, you see what's highest and what's lowest, left over right, and then you'll be able to tell which half cells are going to actually interact. Remember that when something is aqueous, you've also got to circle water, and if there's no oxygen present, then don't choose the one that has water and oxygen. You need all the reactants for it to go ahead. Cool. Then done determining a lot of little typos in there. Determining the max voltage under SLC for the cell from electrochemical series. That is just the voltage at the cathode minus the voltage at the anode, because the anode is reversing. You could also think of flipping the potential on the anode and just adding the two answers that you get, but it's easy just to do cathode minus anode. Done. That'll be only at SLC because the electrochemical series is only at SLC. If they were to do it at any other conditions, they would give you the voltage numbers that you need in the question. Being able to explain how impurities may lead to preferential oxidation or reduction of unintended species. So if you've got something else in there, it may preferentially oxidize or reduce because it may be either in electrolytic closer to the other thing or in galvanic higher up or lower down on the right. So therefore you might have an unintended reaction that is more spontaneous than the other that you wanted, and therefore not get the product that you wanted. Then define a fuel cell and distinguish it from standard galvanic cells. So fuel cells, you don't need to know the specifics of the structure of random fuel cells. I would just know the hydrogen fuel cell is the main one. It's a nice simple one anyway. Definition of a fuel cell. So it is effectively a galvanic cell, but the difference is, how we distinguish it, is it's got the constant supply of reactant and the constant removal of product to ensure that you've got a very high yield and therefore maintaining rate as well. So that's pretty much the main thing. It also doesn't pollute because it produces hydrogen gas, or it produces water, or it produces hydrogen gas and oxygen gas. So they're a much more effective use of chemicals to create electric energy. And the other thing is as well that they're highly efficient. We know that they have almost 100% efficiency relative to, say, 30% efficiency of brown coal, or something like 40 to 60% efficiency of an internal combustion engine. Then explain the common design features. So we've kind of already talked about that. They have they have two electrodes. They usually have a membrane or some kind of permeable membrane to keep the two separated. Sometimes we see an electrolyte being shared between them, but in most cases they'll do a separation. Look out for the ones that have hydrogen gas being evolved or being used, because we know that's highly volatile, highly flammable, takes up a lot of volume, and so therefore is often under great pressure, and there's safety risks with that. So that is a common reason why we keep hydrogen isolated. Then compare the relative efficiency. We've already talked about that one there, so 100%. Compare the safety and storage implications of a hydrogen fuel cell. Again, we've kind of mentioned that. You need to make sure it's under pressure, because otherwise it takes up too much volume. When it's under pressure, it means it's more volatile, and already it has a high level of volatility and flammability as well. So therefore, it needs to be maintained very closely. You often need engineers to make sure they're checking on it, making sure the pressurization is right. And then the storage and transportation of hydrogen is also a very risky move. Then compare the environmental impacts of fuel cells against the combustion of hydrocarbons. So fuel cells have very little environmental impact altogether unless they are requiring electrolysis, which is going to be charged by a hydrocarbon combustion. So they've given an example in the 2017 exam, which I did in a video previously, where it talks about petrodiesel being used in a submarine to help fuel the process of electrolyzing water to then provide the hydrogen and the oxygen to a PEM or a proton exchange membrane fuel cell. Then compare the environmental impact of fuel cells against the combustion. No, we already did that one. Explain chemical reactions using collision theory. So that's it for all of your energy stuff. Now we get into the rates of reaction. So collision theory is the basics of thinking of every single compound or object or matter as tiny little particles moving at high velocity. So therefore, when they crash into each other, collision theory says in order to have a successful collision and therefore a reaction, you need to have the correct orientation, you need to have enough energy involved, and that really comes from kinetic energy, so how fast they're moving, and it needs to occur in the right conditions as well. So as long as you achieve all those things, you get a successful collision. What it also explains is that the more successful collisions you have per second, the higher the rate of reaction, because the definition of a rate of reaction is the number of successful collisions according to collision theory, or it's the amount of product being produced within a given period of time. So we usually measure it by changing concentration per second, but you can also, if you were able to count it, measure it by the number of successful collisions per second. And then that means that when temperature goes up, the particles move faster, and therefore they're more likely to crash into each other, and you have more collisions per second. If the volume goes down or the pressure goes up, then it means that they're in a tighter space, which means there's a higher probability of a successful collision now that they're closer together. And if you increase the concentration by adding more stuff, then you've got a more crowded room, you're going to have more collisions per second. Analyze and explain the Maxwell-Boltzmann distribution curves, which kind of looks at exactly that. So I won't go into detail on that one. Explain the effects of temperature on reaction rate. So we've already gone through that one as well. Explain the effect of surface area. I forgot that one. Surface area to volume ratio. The greater the surface area, the more reactive surface you have, and therefore the higher probability of the reactive surface meeting the reactive surface of another reactant, and therefore increasing the rate of reaction. Explain the effect of concentration. We did that one. Explain gas pressure. We did that one. The effect of a catalyst on reaction rate. So technically we know it just decreases the activation energy, increases the rate of reaction. The reason for that is because a catalyst holds onto a reactant or its substrate, holds it against other stuff and says who wants to react with this, and therefore increases the likelihood of a successful collision. Energy profile diagrams of a catalyzed reaction. I actually already did that before, just that little loop. It does not change the reactant or the product energy levels at all. Then explain what a homogeneous and heterogeneous equilibria are. So these are equilibrium systems, homogeneous or homogeneous, have the same physical states of everything that is in there. So all aqueous, that kind of thing. Heterogeneous, these ones have a mixture of, they might have a precipitate in there as well as aqueous, or they might have gas bubbles or something being evolved. That's it. Pretty unlikely to come up though. So then draw and interpret concentration time graphs of aqueous equilibria. Let's do one of those, and I'm just gonna switch over because the camera's about to cut out, so there'll be a slight delay. And so if we were to look at the concentration time graphs, we have one like this, we have time along here, we have concentration here, and then we have reactants and products. So I'm just going to go with A plus 2B in equilibrium with 3C, like this, right? Just to prove the point. And so the idea is that if we had A, B, and C like this, and then we're going to do some stuff to it, right? So we're going to hold it at equilibrium or whatever it was, then we're going to change things. So what I'm going to do first is I'm just going to add a bunch of C. So that should spike up immediately. And then what would happen is Le Chatelier's principle, which we'll get to, will explain that it will shift the point of equilibrium to the left and it'll favor the back reaction. So we'll see this go down, but because it's got a ratio of 3, it's going to go down quite a bit. It's often best to start with the one that has a coefficient of 1. That would mean that A would get produced, and that would go up by 1 unit. And whatever kind of height I did, and I might just change this here, get rid of that. Whatever kind of height I do here, this now represents 1 unit. So therefore with B, that one's going to gain as well, but it's going to gain twice as much. So it needs to go up twice as much. So it's going to go up by 2 units, like that. That's about it. And then I'm not doing it with a scale or anything. And then they'll give you grid lines to help out with that. And then C is going to go down, but that one's going to go down by 3 whole units. So we'll see that one go down quite a bit, just like that. And then it'll re-achieve equilibrium. And so then you can do those for any given change according to Le Chatelier's principle, which is where we look at this, the effective surface area to volume ratio and reaction rate. No, we did that. Where are we? Concentration time graphs. Distinguish between equilibrium constants. So I might just go through it now because I think it's further down the list. If you increase pressure, this only affects things that are gases. It'll favor the side that has less particles, right? So if these were all gases over here, this side here has 3, this side here has 3. Change in pressure is not going to affect the equilibrium. But if I made this here 2, suddenly this side has 4. So increasing pressure would actually favor the right side, and it's going to favor the forward reaction. So the point of equilibrium will now shift slightly to the right to alleviate that pressure. Lower the pressure, it's going to favor the back reaction to try and increase the pressure, more particles. If they were aqueous though, then the only thing that we really care all that much about is going to be the concentration, right? So if we add or remove stuff, then we're going to add or remove stuff from the left or the right hand side. Think of it as a seesaw. If you raise one side like that, the ball rolls down the seesaw, it rolls to the right, so increasing the left favors the right. Decreasing the right also favors the right. Decreasing the left favors the back reaction, and increasing the right favors the back reaction. And then finally, changing temperature. This is more for exo and endothermic reactions. So exothermic reactions, they prefer colder conditions so they can heat it up, and therefore the forward reaction would be favored in lower temperatures, and then the back reaction would be favored in higher temperatures. And then in endothermic, it's the other way around. They like to cool things down, so they prefer warmer temperatures to go forwards, and therefore cold temperatures will favor a back reaction. Cool. Draw and interpret. We've done concentration time graphs. Distinguish between equilibrium constants and reaction quotients. So with these ones, they're kind of the same thing, but you just use different concentrations for each of them. So basically Q, a reaction quotient, is just the product and the ratio of all of the products and their concentration to the power of their coefficient. I'll stick with these coefficients here, divided by the product of all of the concentrations of the reactants to the power of their coefficients, and then you get some value, right? The K is the exact same thing, but you're using the equilibrium concentrations. So you're trying to work out what its value is at equilibrium. The key thing is, if Q is less than K, then it means that if K is here, Q is still to the left of it, it means that it's still favoring the forward reaction, is still approaching equilibrium. If Q is greater than K, it means that the current equilibrium system is sitting to the right of equilibrium, and it is favoring the back reaction as it tries to shift to the left. Once Q is equal to K, it means that we're now at equilibrium. That's pretty much it. You can also predict the units because you can just put molarity in all of those little places, and you can use your index laws, and you can see then that you'll get M3 over M4, which is M to the negative 1. Oh, like that. And then that gives you the units. Cool. Determine the units, we did that one. Explain Le Chatelier's principle, I've kind of already gone over that, but the definition of it. So it suggests that when an equilibrium system is unbalanced by some change, it will attempt to resist that change or really partially oppose that change such that it will favor a forward or a back reaction that will help oppose or partially oppose that change. So it's very wordy, but everything that I went through before with volume, concentration, and temperature, those are the 3 that you want to know. Remember that catalysts do not change the position of equilibrium. Then they only change the rate. Use Le Chatelier's principle to explain reaction system response to change in temp. We did that. Change in pressure, change in concentration. Being able to predict factors that will maximize yield versus those that maximize rate. So rate is maximized by high temperature, yield is maximized based on Le Chatelier's principle. The biggest one is the trade-off, which is the next one in exothermic reactions, because yield-wise, an exothermic reaction wants low temp, so it can heat it. Rate-wise, it prefers higher temperatures. Every reaction will go better in higher temperatures according to collision theory. So therefore, exothermic reactions have a bit of an issue. If you're trying to run a factory and you're trying to make something and it's an exothermic process, you'd want to raise the temp so you can increase the rate of reaction and make it fast. The problem is that will favor the back reaction and you won't get a high yield of your product. So then you want to lower the temperature, but then you lower the rate. So you have to find some happy medium in between. And then explain the elements of electrolytic cells. So electrolytic cells, we kind of went into that before. It's the reverse of a galvanic cell. So you're plugging in a power source, an electricity source, and you're using that electric energy to reverse or charge the system or the cell in a non-spontaneous direction, right? You're still getting oxidation and reduction, but it's costing you energy now to do it. Using the electrochemical series to determine suitable solutions as electrode materials. So that just means basically making sure that you're using a solution and an electrolyte that is not going to preferentially oxidize or reduce. So what that means is once you've got your target species, this time you want right over left, might be inverted on the camera, hopefully not, then that means that you don't want to choose electrolytes or solutions that sit between them because otherwise they may preferentially oxidize or reduce. And then you won't get your reaction. Predicting half-cell reactions from electrochemical series, literally the exact same thing. Now we want right over left though and closer together so there's a smaller energy gap. Understanding the impact of preferentially electrolyzed species means that you don't get the product that you want. The comparison of electrolytic cells to galvanic cells in terms of their energy transformations, this time it's electrical to chemical, the complete reverse. Their features and their processes, everything the same as galvanic. You've still got the wire, you've still got the salt bridge and all the rest of it, except now you've also got a battery attached to it. And then stoichiometric calculation of amount and mass of product, time or current used in electrolytic cells using Faraday's law. So this Faraday's law is that Q is equal to IT and Q is equal to NF. So we can just say IT is equal to NF, where N is the number of moles of electrons, F is Faraday's constant 96,500, T is time in seconds, and I is the current in amps. Like that. So basically you deliver an amount of electrical charge and you use that to mobilize a number of moles of electrons. That is basically it. So then, where are we? 1, 2, 3, cool. And then stoichiometric calculations of amount and mass of product time. So I actually forgot the stoichiometry of it. So generally speaking, you start here, you get your number of moles of electrons, that's going to be IT over F. Then from there, you can go number of moles of pretty much any species that is in your half cell or overall reaction. And you can just do a mole ratio multiplied by the number of moles of electrons. Now you're into the basic stoichiometry at that point. The electrolytic element is now gone. We usually use electrolysis to try to electroplate things, so put a thin layer of a metal over the top of another material. So in things like jewelry, we can electroplate gold, so gold plated, that kind of thing. But you can also plate metal onto things to protect them from corrosion or oxidation. It's done in cars, it's done in little bits and pieces, done on phones, all kinds of stuff. Then the comparison that's done. Stoichiometric, the importance of allowing species to migrate between electrodes in secondary cells. So if you're not able to let them migrate back and forth between, you can't recharge it. And that's it. So the biggest problem with the lead acid accumulator in a car battery is that a lot of the lead sulfate that's produced in the galvanic discharge of the battery while it's operating actually escapes onto the terminals, and then you can't actually get it back to electrolyze it and recharge the battery, which is why car batteries often go dead after a while. Even though technically when you're running it, you're using the fuel of the car to actually then harvest some energy and then recycle and charge the battery while the car is running, right? But if you're losing product in the process, it can't become reactant for the recharge process. So if you have any questions where it talks about the fact that something is escaping, then it means you're not going to be able to recharge that battery. Carbon's valence and its relation to hydrocarbon bonding structure. So it has a valence of 4, which means that it can form 4 bonds or 4 attachments. Generally speaking, we see those 4, but obviously 2 of the 4 could be made up of double bonds and that kind of stuff as well. Ability to draw structural isomers of a given compound. So you're dealing with the same number of carbons, hydrogens, and oxygens. You're just shuffling them around. And technically speaking, structural isomers, you're kind of rearranging the carbon chain and maybe turning a chain into a branch chain instead. So you just kind of move the first carbon to the second carbon, move it to the third, the fourth, until it hits the middle, because then it becomes symmetrical. Then try moving two of them in different arrangements, and then also doing ethyl chains and stuff like that as well. That's about it. The study design actually says you're not expected to know anything beyond 2 branches or 2 functional groups, so the structural isomers shouldn't be all that complicated. Identify and count chiral carbon. So a chiral carbon is a carbon in a stereoisomer, an optical isomer. These have 4 uniquely different attachments to them on each of its 4 bonds. If it doesn't have 4 bonds and it has a double bond or anything, it cannot be chiral. So look through the carbons that are sp3, or I can't say sp3 hybridized, that's a unichem. Look for the carbons that have 4 different attachments, including alkyl groups and that kind of thing. If all 4 are different, it's a chiral carbon, or a chiral center, sometimes referred to as. Distinction between cis and trans isomers. So we see this in double bonds. So basically cis means on the same side. So we'll see this, whereas trans, you'll see this, like that, Z versus C, done. Then comparing bond strength of carbon-carbon single, double, and triple, it goes decreasing order of strength. The single bond is the strongest, that's why it's really hard to actually remove. Double bonds are a little bit weaker, you can break the double bond and turn it into a single bond by saturation. Triple bonds are even weaker, you can access them. We don't really see triple bonds all that much. Draw molecular structure of compounds. That one's just drawing them out. I mean, do full structural is the easiest. Then draw skeletal structures. So remember, these ones don't have hydrogens shown if they're just hanging off of the carbon chain, so watch out for that. And then draw semi-structural. That's where you group methyl groups. Instead of saying C with 3 branches of hydrogens off of it, just say CH3, CH2. And if there's multiple CH2s, you can just have CH2 in brackets with the number of them that there are. So that's semi-structural. And then draw structural structures of compounds. That's what we were talking about before. Distinguish between alkanes, alkenes, alkynes. So they're your 3 homologous groups. Alkanes, all single bonds, saturated. Alkenes, at least 1 double bond. Alkynes, at least 1 triple bond between the carbons. Benzene is technically just a 6-carbon ring with 3 double bonds around it. And then haloalkanes, an alkane with a halogen attached, like a chlorine, fluorine, iodine, or bromine from group 17. Primary amines, these ones just have an NH2 or an amine group on the end of the carbon chain. That's why they're primary. Primary amides have double bonded oxygen NH instead. And then alcohols, these ones have just OH. They can be primary, off the end carbon. Secondary, meaning off of a middle carbon. Tertiary, meaning off of a branched carbon. And then aldehydes, these are, again, a bit of a dead end. They're always on the end of a carbon chain, so they don't have the word primary because they can't be in the middle. These ones, just like this, that's your aldehyde. Ketones, these are double bonded oxygen in the middle, on like that, the middle of a carbon chain. And carboxylic acids, I'm sure you'll already be familiar with that. So carboxylic acids, do it over here, looks like this. And then esters is when you get a primary alcohol and a carboxylic acid. So that is where you see cook, like that. And there's that there, right? Cool. Then IUPAC naming up to 8 carbon compounds. They're not going beyond 8 or anything like that. So you go through, first thing is get your carbon chain, check that it's an alkane, alkene, or alkyne. Number it closest to the double or triple bond if there is one. Otherwise, number it closest to the branchings. And then otherwise, number it closest to the functional groups. All the functional groups and everything, obviously they all have different names. I can't really go through every single one of them. But remember that you have to put the carbon number that they're attached to, unless it is on the first carbon and there is nothing else there, then you can just kind of say it. So if it's like a primary alcohol, then you can just say methanol or like propanol or something like that. You don't have to say propan-1-ol. Then explain the trends in boiling point and viscosity of hydrocarbons in relation to their structure and bonding. So generally speaking, we see when hydrocarbons have longer chains, their boiling point goes up because there's more bonds to break. If they're shorter, then they have a lower boiling point. If they're saturated, they have higher boiling points because double bonds and triple bonds are weaker and easier to separate. And the same thing with viscosity and that kind of stuff as well. So most alkanes, though, are usually gaseous, so you'll usually see they're like a little bit thinner, whereas as you start to get into kind of long carbon chains, they'll start to get thicker and more viscous. Then define flashpoint and explain how it relates to structure and bonding. So flashpoint is the lowest temperature at which the fumes of a hydrocarbon can then ignite with an ignition source. So the idea is, in terms of safety, low flash points is really dangerous because it means lower temperatures can still ignite it. Higher temperatures would be higher flash points. They're a little bit safer. So petroleum actually has quite a low flash point, which is why you don't want to use your phone or light a cigarette or light a match or anything at a petrol station, because the fumes actually have a relatively low flash point. Oxidation of primary and secondary alcohols. So now we get into all of our organic pathways, which I'll quickly scribble down. So oxidation, primary alcohols, these ones are the most fun. They love this. Onto an R group. So basically when you do that, so you might have like dichromate, for example, with sulfuric acid, and then it'll oxidize into an aldehyde like this, and then it'll oxidize further. You can actually get another layer out of it. It'll oxidize into a carboxylic. This is the final end point, like that. If you have a secondary alcohol, it means that it's got carbons on two sides, right? So it's in the middle of the chain. You can still do the same reagents and everything. This time you get a ketone, but notice that there's no opportunity to add any more oxygen to it. Everything's all taken up. And if you look at tertiary, they don't even react under oxidation because there's nowhere to put the double bond. Because if you tried to put this as a double bond, you'd be breaking the rule of the 4, right? So that one cannot react under oxidation. Then substitution of haloalkanes. These ones are pretty easy, these ones here. So if you have a halogen, doesn't really matter where it is. There it is there. If we put in sodium hydroxide or something, the hydroxide will attack, remove this, that'll go with the chlorine, and the hydroxide will take its place, and you can make an alcohol. There you go. You can also do that with water in acid. The acid is just there to separate the water into hydroxide and protons. Then addition of alkenes. This is where we look at like polymerization. Add two alkenes together, it saturates the double bond, and then they make a single bond, you get an alkane. Hydrolysis of esters. So this is splitting ester bonds with water. Hydrolysis means hydro, water, lysis, to split. Splitting with water, you take the ester, you add the water, and you split it. It goes back to its carboxylic acid and its primary alcohol. Condensation, the formation of an amide bond. So this is where now you're making like a peptide bond between two amino acids, for example, and you've got a primary amine and a carboxylic. They glue together, water comes out under condensation, just like esterification, but then you end up with a nitrogen attached, and that makes an amide bond. Calculation of atom economy. So this is just the percentage of atoms that go in that are actually put into the actual product. So it's a measure of your usefulness, or like a measure of the wastefulness of the process. If you've got 90% atom economy, it means 90% of the atoms that are reactants are actually being put into a usable product. You can calculate it as well. So it's literally just like number of atoms used in the product divided by number of atoms that go in, times that by 100. There's your atom economy. Then explain how mass spec works. So with mass spec, I won't go through these in massive detail. The chances of them asking about the detail, very, very, very slim. Mass spec though, you're fragmenting an unknown sample, fragments it into its molecular ion and a bunch of other smaller little fragments and ions. They go through a channel with a magnet. Because they're all charged, the magnet actually bends them. They bend through a path, they hit a signal, they hit a detector. Based on how much they bend, we know about the relative ratio of their mass to their charge, and we plot those on a mass to charge ratio. That gives us our readout of the abundance of the different types of fragments. From that, we can start to work out the mass numbers of all the different fragments, and therefore the mass number of the entire sample without knowing its full structure. And that's the interpretation of it, right? So generally speaking, you'll have one which has a really, really high mass to charge ratio. That'll be your molecular ion peak. Watch out for TMS. That is just there to set 0. And then you'll have determining mass number and identifying small fragments. You'll get little fragments along the way. You'll often see 15 and 29 because they are methyl and ethyl groups. Explain how IR spec works. So IR, you're using infrared radiation that is causing vibrations in the bonds. They do things like they scissor, they go this way, that way, they wag, blah, blah, blah. And these all have different wave numbers associated or detections, and that relates to the bond angle and length, which relates specifically to the different types of bonds, whether it's a carbon-carbon single bond, a carbon to hydrogen, a carbon double bond to an oxygen, and so on. And you check that against all the wave number data in the data booklet, and then you can work out all the bonds that are available. Still doesn't fill in the full picture though. So then explaining how NMR works. So this one, you're using nuclear magnetic resonance, which is relating to the spin frequencies of the electrons being upspin and downspin, interacts with those. We've got carbon NMR and proton NMR. Carbon NMR tells you about the arrangement of the carbon atoms, so therefore the carbon chain and whether or not it's branched. The proton NMR is a little bit more specific. That tells you about the hydrogen environments and how the hydrogen is arranged, which can be really, really fine-tuning your understanding of the structure of it, as well as determining functional groups and their positions. The peak area underneath tells you about the relative abundance or the relative number of hydrogens that are in that particular hydrogen environment. The splits tells you about how many neighboring hydrogens there are. So we use the n+1 rule. If you've got 3 neighboring hydrogens, then it means you have 4 splits, right? And you'd have a quartet is what it would be described as, and so on. Then we have determine the structure of a compound from all spectroscopic data. So each of them tells you something. You put all that together, you can then make the structure. Those are really tricky though. They'll always have a big one in there. Just make sure you do a few of them in a row to get really comfortable with reading the data and interpreting it. If you just draw out all the bits and pieces, then you just play kind of Lego with it, or puzzle pieces, glue them together, and you'll be able to get the structure. Make sure it matches with all of the different readouts. HPLC is the only type of chromatography still examinable in the study design. So with this one, you're trying to work out constituents, not necessarily structural elements. And so there you're looking at its affinity for the stationary phase versus the mobile phase, usually using an aqueous solution. And the mobile phase is the thing that is moving through, usually a liquid. The stationary phase is usually going to be some kind of pad or something, which we're trying to see if the constituents will adhere to based on their polarity or their chemical properties. The longer it takes for it to come out means the more it had an affinity for the stationary phase, versus the faster it comes out, the less affinity it had for it, and the more affinity it had for the mobile phase. That helps us separate everything and isolate and go, okay, that's coming out in 3 seconds, so therefore that must be this particular compound. And we can determine the makeup of a particular sample. Calibration curve to determine concentration in a solution. Those are really easy. You just read them backwards. So there's no trickery in them. They'll give you a calibration curve. It'll have over here abundance, or it might have something else, might have absorbance or something like that. You find the absorbance given in the question, you read it backwards. Be nice to add a line on there. You read it backwards, and then it'll link to a concentration. And then you use that in your stoichiometry. Explain how a titration works to determine the concentration of a solute in solution. These are quite tricky. They're not doing back titrations anymore, thank God. So forward titrations, basically you have an aliquot and you have a titer. So you have a known standard solution, which usually goes in the burette with a known concentration. You then have an unknown concentration sample, which usually dilutes, so you've got a really sensitive sample. You put that into the volumetric flask, usually about 20 or 25 ml aliquots. You put that in, you drip in the standard solution from the burette, you swirl it around to make sure everything's good. You'll have an indicator in there which will change color when the endpoint hits, and therefore you know when you've usually neutralized an acid with a base or a base with an acid. That will then allow you to work out, in terms of the calculations, always start with number of moles from the burette, from the stock solution. You can always get that because you've got concentration and then the average volume of the concordant titers. Then from there, once you get the number of moles of the thing from the burette, then you can do mole ratio, get the number of moles of the thing in the sample, the acid or the base. Once you've got that, then you can get the concentration in the aliquot by dividing that number of moles by the volume of the aliquot. Now you've got the concentration. Then you can backtrack that and multiply that by a dilution factor to get the original concentration of the sample. Then that's all good. Where was I? Titration, and then food chem. So protein structure, including peptide links, primary, secondary, tertiary, quaternary. So amino acids glue together to form polypeptides. This then folds into a complex structure. Primary is just the linear sequence, is a good way to put it, the linear sequence of amino acids glued in by peptide bonds between the carboxylic ends and the amine containing ends of each. Secondary is where then the side groups start interacting. They start to make flat two-dimensional planar sheets of either beta sheets or alpha helices, and they usually go in layers of alpha and beta helices. Tertiary is where that then folds in on itself and the functional groups of each start interacting, and then you've got things like disulfide bridges and that kind of thing starting to form, although they can happen in the secondary, I should say. And then tertiary, it's folding into three-dimensional structure. most proteins stop there. Quaternary is where you've got multiple three-dimensional domains, which then glue together into a functional complex. We no longer call it a protein, you call it a protein complex at that point. Best example is hemoglobin. It's got 2 alpha subunits, 2 beta subunits. Glue them together, makes the heme group, which can then house iron to then hold oxygen to transport oxygen around the blood. Distinguish between essential and non-essential amino acids. Whenever you hear essential and non-essential, essential means that we cannot produce it in the body ourselves, which means we require it from diet, therefore it is essential. Non-essential means that we can produce it ourselves, and therefore we don't necessarily require it from our diet. Explain the zwitterionic properties of amino acids. So zwitterionic just means that it's ambidextrous. It can be both acidic or basic, depending on who it's with. When it's in water, you have both the amine group being an NH3+, and the carboxylic group being COO negative, i.e. it's both donating and accepting a proton on itself. If you put it in the presence of an acid, it'll go, cool, I will be a base. We'll see then that it won't donate its proton, so the carboxylic end will have the hydrogen, and the amine group will be an NH3+. Vice versa, if you put it in the presence of a base, it'll act as an acid, it'll keep NH2 on one side, but it'll donate a proton to the base from its carboxylic end and be COO negative. Look out for the functional groups, because if they have any amine groups or carboxylic groups, you also have to adjust them as well. Determine the structure with charges. We did that one just then. Carbohydrate structure, including distinction between monosaccharides, disaccharides, and polysaccharides. So carbs, our main source of energy, although they're not the most energy potent, and monosaccharides are just single carbon rings, like glucose and that kind of thing. Disaccharides have 2 rings to them, and then polysaccharides have many. Explain the formation of a glycosidic link. So this is where you have 2 alcohol groups or hydroxyl groups joined together, kind of like a condensation reaction, but you don't actually get water out of it because, you do get water out of it, but there's no double bonded oxygen to make an ester. So you just end up with COC, and that is an ether link, but they've cut that from the study design. We just need to know it as a glycosidic link. There is an alpha link, which is where both of them are on the same side. And then beta, where one was pointing up, one was pointing down, and so the glycosidic link goes on a zigzag and makes a Z shape. And then explain how glucose, terrible spelling, is stored as glycogen in the liver. So we just package glucose together, 1, 2, 3, into a big branch network, and we store that as glycogen molecules in the liver, and then we clip it back off in gluconeogenesis to get the glucose back into the bloodstream whenever we need it. Compare glucose, fructose, sucrose, and aspartame with reference to structure and energy content. So aspartame in particular is an artificial sweetener. We don't require quite as much of it. It's relatively energy potent. We're not really using it for energy. We're just using it for a sweetener, if anything. It does not have the standard carbohydrate structure. Glucose, fructose, and sucrose, relatively high energy content. The difference is glucose is what we actually metabolize. So this is the best one if we want fast metabolism. Fructose is a very, very sweet sugar, has a relatively high energy content, and so does sucrose as well, but we need to process these a little bit more if we want to metabolize them. Fats and oils, structure including ester linkages. So fats and oils, we mostly look at triglycerides. We've got 3 fatty acids, which really just have carboxylic ends. They then esterify, or they condense and glue to a glycerol molecule and make a triglyceride. And so they have the most energy per gram. From memory, it's 37 kilojoules per gram, whereas carbohydrates is only 16 per gram and protein is 17 per gram. That's all in the data booklet anyway. And the camera's going to run out again, so I'm just going to switch it. In terms of the structure, triglycerides, 3 fatty acids glued to a glycerol. You can hydrolyze them and cut them back off, and then digest them for energy. We can convert them to glucose, put them into the glycolysis process. Determine relative melting points of fats based on the degree of saturation. So if they're more saturated, higher melting points, which means that it's a little bit harder to metabolize. So we generally want to keep our saturated fats relatively low in our diet, although not completely non-existent, but they just metabolize slower and they're less preferenced. Unsaturated fats are a lot better. Polyunsaturated means many double bonds in there. Monounsaturated means 1 double bond, and so it's a sliding scale. The more unsaturated they are, the more double bonds, the easier it is to metabolize and break them down, and therefore they have lower melting points. Simple example is you could look at a solid fat on a cut of steak. It's going to be about white solid fat. That is going to be saturated fat, whereas polyunsaturated fats and monounsaturated fats are going to be like your cooking oils, olive oil, linseed oil, that kind of thing. They don't solidify at room temperature. Distinguish between essential and non-essential fatty acids. So same thing, these are fatty acids that we either can make, that is non-essential, or can't make, they are the essential ones that we need to get from our diet. Compare and identify the structures of omega-3 and omega-6 fatty acids. That is the position of the double bond. Omega-3 is the double bond that is 3 carbons away from the most high oxidized end. Omega-6 is 6 carbons away. Omega-6 are a little bit easier to break down because when you have a kink in the chain further up, it means that you've got less density because it's pushing everything away, lower melting point. They're both pretty helpful to us though. Vitamins are essential as a micronutrient due to the inability to produce them, except for vitamin D, it's the only one that we can produce. Fat soluble versus water soluble. Fat soluble vitamins need to be absorbed with fat from the gut. Vitamins that are water soluble can go straight with water. In terms of supplements, vitamin D, vitamin K, these are fat soluble, so you generally need to take them with food so they get absorbed properly. Vitamin C and that kind of stuff, it's water soluble, so you can just take a supplement and it'll be absorbed immediately. The downside is water soluble means it comes out in the urine really quickly. Fat soluble, we can store it a little bit better in the body. Explain the general process of metabolism of food. So we've got in the mouth mechanical, which is the chewing of food, and then or mastication. Careful with what you're actually saying there. And then the other one is enzymatic. We've got amylase in the mouth, which is breaking down carbohydrates into disaccharides, which is why when you put like a salada on your tongue, it starts to taste kind of sweet. If you leave it there to go gross in your mouth, then it goes down the esophagus into the stomach. Then you've got mechanical again, because then you've got peristalsis of the stomach, and you've also got chemical digestion from the stomach acid, and a little bit of enzymatic as well, because you've got enzymes like pepsin which start working on it, moves into the small intestine. You've then got the bile from the gallbladder being squirted in along with a bunch of other enzymes, and the small intestine then has enzymatic and mechanical breakdown. And then finally, when you get into the large intestine, you have bacterial digestion, because then you've got our gut flora and fauna, or flora, which is going to help break down fiber, because we're not very good on our own at doing that. Explain enzymes as protein catalysts. So anyone who does bio probably already knows a lot of this. I'll try to move pretty quickly because this is well and truly over an hour now. Explain enzymes as protein catalysts. So enzymes are just catalysts. They are specifically protein molecules that act as catalysts to lower the activation energy and raise the rate of a reaction. The role of an active site is to bind the substrate in order for it to work. The lock and key model suggests that the active site is fixed, and so you need a substrate that is specific and complementary to that active site. The induced fit model is an alternative, which says that the active site kind of roughly fits, but then molds to it like Play-Doh and then reforms again later. So it's a little bit more of an adaptable model. The effects of change in pH and temperature. So if you lower temperature, it just makes the enzyme go dormant, but it can come back again. If you raise temperature, it denatures beyond its reasonable range, and then it can no longer be returned. pH, if it goes too low or too high, either way it's going to denature it. You got to keep it within its optimum ranges. Explain the structural changes that occur. Key thing is primary structure is not disrupted during denaturation. It's the secondary and tertiary structures that are disrupted, which means that interrupts the active site structure. So therefore it's no longer functional. Discussion of the body's inability to hydrolyze cellulose. We just have to know we can't hydrolyze cellulose, which is why we can't digest corn properly. Then define the glycemic index as a ranking of foods based on metabolic energy release. It kind of says it in there. Low GI means you burn it slowly. High GI means it burns really quickly. Relative energy content of protein, carbs, fats, and oils. That's already in the data booklet, but protein 16 grams, 17 kilojoules per gram. Carbohydrates 16 kilojoules per gram. And then fats and oils 37 kilojoules per gram. Oxidative rancidity. This is what happens when you get oxidation of fats and oils and you end up with free radicals. It effectively is when an oil goes off after it's used by dead or is kept open. That's why you always need to keep them stored in closed containers. Coenzymes are not necessarily enzymes themselves. They're often minerals and metals. These help an enzyme do their job. For example, iron is a coenzyme to hemoglobin. Write a balanced thermochemical equation for cellular respiration of glucose. So respiration, it's glucose, C6H12O6 plus O2, 6O2, and then going into water and carbon dioxide. So water and carbon dioxide. So 6 waters and 6 carbon dioxide. Haven't said it out loud, I always write it. Then explain how calorimetry works. So this is the basics of you burn a fuel sample, which is usually food. If we're looking at food chemistry, you're trying to work out its energy content. You use that to raise the temperature of water. You use MCAT to work out the energy released. You divide that by the mass of the sample, and therefore you've got the energy per gram, and you can quote that as per 100 grams and put on the nutritional information. If you have an inefficiency, you've got to make sure you divide the energy by the efficiency level. So if it's 30%, divide your energy by 0.3, you'll get the actual amount of energy. And I'm just going to go without the camera now because the battery's died, so I'm just going to finish this one off. And then compare solution and bomb calorimetry. Solution calorimetry if you're not dealing with solids, bomb calorimetry if you are. Calculate a calibration factor, that is VIT divided by delta T. So voltage times current times time in seconds. That'll get you your energy given out by the battery, which you're using to calibrate the system. Divide that by the energy change, delta T, and then you've got your energy per degree Celsius, which means you don't have to worry about adjusting for mass anymore. And then finally, stoichiometric calculations for energy content in a food sample from calorimetry. We kind of went through that before, but once you've got your energy per gram, then you can multiply that by 50 grams, 100 grams, whatever you've got, and then you can get the calculations there. So hopefully that's all been really helpful. That is a relatively rapid run through. I think it's like close to an hour and a half. That's the entire chemistry course though. So hopefully this has been helpful. I'd probably recommend making a list similar to this so that you can just kind of check stuff off before Tuesday, go through a few assessment reports, check that you've got everything in place. But otherwise, good luck for Tuesday, and I will let you go because I have to run to another tutorial. All right, see you later, guys.